Hello and good morning to all viewers. Today our group want to present about smart condition monitoring in CNC machining. Okay, next for our group members. My name is Muhammad Idam Zaki. My members is Muhammad Azmin, Marcelinos, also Harry. Alright, we go to the introduction. Alright, for introduction, this experience focus on smart condition monitoring in CNC machining using vibration, noise, and temperature sensor to monitoring machining condition in real time. The main purpose is to detect machining instability, especially chatter, which can affect surface quality, tool life, and overall machining performance. For, for objective, monitoring vibration, noise, and temperature during machining, identify chatter threshold for different materials, compare milling and lathe machine performance, evaluate material behavior under different cutting conditions. Alright, next experimental overview and machine setup. They have a two table. It's called average RSM value for milling, also for lathe. Alright, milling and lathe machine use material telephone, aluminium, mild steel. RSM vibration measured at different DLC. Chatter threshold is RSM to 0.7 G. Vibration increase as DLC increase. Higher cutting force to higher vibration. Lead becomes unstable early than milling. Okay, we go to the next slide. Individual graph. This average for the result. The milling graph show a smooth and steady increase in vibration, remaining below 0.7 G on the higher depth where it reached 0.7145 G at 1.5 mm, also 0.78 at 1.7 mm DLC. Next, for the aluminium, RSM increase steadily up to 1.1 mm, then rise sharply at 1.3 mm before slightly decreasing to 0.746 at 1.5 mm due to chip clogging. I will let to my friend Marcel to continue the explanation.
Okay, thank you, Brother Am. Now let's observe the trend on the LED machine. This is the LED machine. We see that the Teflon see steady climb from 0.2465 gravity, and then Spike Lee sharply passed at 1.0 mm DOC to cross the threshold at 1.1 mm, eventually peaking at 0.8347 gravity. And then for the aluminium is follow an identical climb pattern, increasing steadily before rising sharply after 1.0 mm DOC to peak at assembly like a Teflon. Is it is 0.8347 gravity at 1.5 mm. And for the my steel is display the highest baseline vibration overall. It is increased rapidly due to immense cutting force crossing the chatter threshold early at hitting 0.84 at 1 gravity at 1.3 mm deep of cut. And for the combine, the lead machine is when comparing the two system, we notice distinct curve characteristic. Why are they different? You see why are they different? Why they different? Because it come down to the cutting machine. And for the lead is operate via continuous tool workpiece contact which generate continuous cutting force and accumulate structural vibration faster causing the machine to chatter early. The lead is the chatter is very early than milling. Conversely, a milling machine relies on intermittent cutting because the tool engagement is interrupt is yield lower overall RMS vibration value and delay the onset of chatter until later stage. Next, we pass to the Harry uh, for the next slide lah. Okay, thank you.
Okay, thank you to Marcelino. Next, the material behavior. Material property. This is the table of the material property. Think, why do this material is hybrid? Vastly different. Chatter threshold. It is heavily dictated by their stiffness and slipping capacity. It is the method properties and this is the explanation. Okay. For the mainstream process high stiffness but low damping is transmit the vibration energy efficient through the structure making it susceptible to chatter. Teflon sit on the upside and it has low stiffness but very high damping. It absorbs and dissipates structural energy efficiently delay. Chatter onset. Aluminium. We present the middle ground balancing moderate stiffness with the moderate damping. And this is the why do material produce different chatter threshold for mainstay, aluminum, and Teflon. This is the relationship, and this is the explanation. Okay, next. For the next is noise analysis. Okay. Beyond noise level base, we are seeing graph for milling and lead data table. Okay. Beyond mechanical vibration, we track the acoustic domain using noise sensor setting a critical workplace safety threshold and at 5 dB. Orbital discovery in this experiment is that noise level beats the critical threshold earlier than vibration. For example, during my milling, noise surpassed at 5 dB at 1.3 mm DOC, whereas vibration wait until 1.5 mm to cross its line. This for noise serves as an excellent early warning indicator for machining instability before mechanical chatter fully developed. And this is the table of material milling, milling for our material, and this is the graph. And this is for lead. This is the analysis, noise analysis relationship between vibration and noise, and for milling machine and lead machine. And this is the explanation can noise be used for chatter detector. Okay, next is the temperature analysis. Temperature rise versus the OC graph text explaining lagging indicator. We look at the thermal domain. Temperature rise gradually as a direct result of accumulated friction and cutting force. Generally during machining, however, unlike noise, temperature acts as lagging indicator. It takes time for heat to physically build up, meaning it responds after mechanical and acoustic shift has already occurred, while it is either for instance for detector it is critical crucial for confirming alternate machining lag. I will know. Okay, hold on. This is the table for table temperature analysis from milling machine and all material. This is the graph. And this is the lead machine for the lead machine. Next, I will now pass the presentation to Azmin to wrap up with sensor reliability and our final comment. Okay, thank you.
Thank you to Harry. By mapping out the sensor ecosystem, we clearly see the order of trigger events. Vibration change are immediate, noise reaches its threshold next, and temperature follows as heat accumulates. Utilizing all three sensors provides invaluable data redundancy by combining the mechanical, acoustic, and thermal domains. This multi-sensor approach protects the machine from single-point sensor degradation and significantly reduces false alarm triggers on the shop floor. Based on our finding, we have calibrated distinct green, yellow, and red alarm zones for production safety. We strongly advise against utilizing a generic baseline or a single fixed DOC, such as capping all material strictly at 0.8 mm or 1.0 mm. Doing so forces a massive sacrifice in the material removal rate (MRR) for resilient setups like Teflon or aluminum on a leg. Instead, we recommend material-specific DOC parameters. Calibrating optimized threshold to match each material physical attributes allows us to exploit higher feed rate capacities, maximize spindle throughput, and extend tool life. This is stable for comparison milling and lathe, which machine stated earlier for Teflon is milling, for aluminum and mild steel it is lathe machine. To conclude today's presentation, let us review our core engineering takeaways. First, material stiffness and damping profiles strictly dictate chatter resilience. Second, harder material like mild steel and aluminum reach chatter much earlier on a continuous contact lathe 1.3 mm than on an intermittent milling machine 1.5 mm. Plus, integrating an robust multi-sensor ecosystem provides the high fidelity feedback loop necessary for automated Industry 4.0 environment. Thank you very much for your time and attention. We'd like to open the floor to any question you may have.